Hello, everybody. My name is Ryan Schewel. Welcome to my data science and machine learning channel, and I do advanced analytics as well. So in the narrative today, I want to talk about how to optimize public bus frequency with different passenger flows, and we're going to forecast into the future how to manage this whole process, right? If we add more buses, this could be more expensive, and people will be picked up quicker, right? But there'll be less people on each bus, so you don't really utilize the bus to the fullest extent possible. And if you don't run buses so often, there's going to be a lot of people waiting around unnecessarily, and they're probably going to be becoming frustrated, especially this time of year. It is, December 5th. It's getting pretty cold in New York City, and people don't want to be outside waiting 1 hour in frigid cold weather for the bus to come. So how do we do this, right? We want to reduce overcrowding on buses, avoid running empty buses. We don't want that. We want to improve on-time performance, right? That's the opposite of empty buses. Make rider experience better, right? So enhance the overall experience for riders. Use limited fleet and driver resources to the best capacity possible, right? Lower emissions, less fuel consumption, less costs, right? So more cost effective. Support equity and accessibility goals. Make this non-biased for some kind of who knows what people come up with, gender or race biases, things like this, right? We want to try to eliminate any possible conceivable characteristic of bias, right? So that can be another goal. Better planning, forecasting, building a foundation for real-time adaptive transit, right? Using machine learning, deep learning techniques like this, and basically save millions of dollars in annual operating costs, and everybody's happier, right? Win-win-win. Happier riders, happier bus drivers, and happier public transit governance system, or whatever you want to call it, right? Because they save money. So let me go ahead and get this thing kicked off. Okay, so we're going to have our range of dates and times. We have hour. DOW is short for day of week. We're going to say if less than 6 a.m. and less than 9, this is pretty much going to be peak rush hour. If less than 16 and less than 19, this is kind of going to be evening peak. Otherwise, it's going to be off peak, right? So we have 2 peaks during the day, one in the morning, one in the evening. Both are rush hours, right? And we're going to have off peak as well. So we're going to try to plan around that kind of capacity or that kind of demand, and the capacity of the bus and the demand of the riders, right? So I just ran this. So we have the date, the time, hour, day of the week, right? So this is 1200 hours. That's midnight, 1 a.m., 2, 3, 4. Day of the week is just going to be 0. So 0 is actually Monday. So in Python, 0 is Monday. It goes 0 through 5, Monday through Friday. 0, 1, 2, 3, 4. 4 is Friday, right? 5 is Saturday, and 6 is Sunday. And then you restart with Monday. Monday is 0. So Python is always 0 based. You can change that and make Monday 1. You can make Sunday 1. But by default, Monday is 0. Fridays 4, 5, and 6 is Saturday and Sunday. That's how it works, okay? So let me go ahead and run this. We have Facebook Profit. This is a very powerful forecasting tool for time series analysis, right? You can check this out. You can do all kinds of research on Profit. I have several videos about this on my channel. So if you really want to learn more about Profit, machine learning tool. And just Google it. You can find a ton of information. And I have a couple videos on my website that describe exactly what it is, how it works, how to implement it, and so on and so forth. So with Profit, you need a few variables, and actually just a few. It's only going to take a handful of things here. Daily seasonality, weekly seasonality, and yearly seasonality. So we have to accommodate for those. And we're going to import this into the Profit model. Originally, this came from Facebook back when we used to have Facebook. Now I think everything is called Meta. They changed the name to Meta for some reason. I'm not sure I totally understand that, but whatever, they do whatever they do. And there's basically 2 inputs to this Profit model, right? So you have X, which is basically the date, and the Y is the item that you're trying to forecast. So in this demand, in this case, it's going to be demand for buses, forecast passenger demand 1 week ahead, okay? So you set this up, there's literally just 2 inputs in the Profit, the date or the time, right? It's time series. It's going to be some type of metric that we analyze over a period of time. It can be hours, it can be days, weeks, months, years, something like that. It has to be one element of time, and the y hat is what you're trying to predict. So this is the independent variable. This is the dependent, right? So this right here is dependent on this. And if you think of this practical example, just like at rush hour, right? During rush hour, the x ds, this is the data series or time series, whatever you want to call it, the x is going to change. It's going to increase during the rush hours, the peak rush hour in the morning, peak rush hour in the evening. And based on that peak or that change in demand, we're going to make a prediction of how many people are going to need that bus. That is passenger demand, right? So hopefully that makes sense. This is what the chart looks like. I just plotted that. You can zoom in, zoom out. You can see the time series over here, and you can see that this is pretty consistent and repeatable, right? So based on the time of day, right? This is 1800 hours, so this is like 6 p.m. in the evening. This is about 7 o'clock in the morning. Every time it's morning peak and evening peak rush hour, it spikes up, and overnight it goes down. In this case, goes down to almost zero. This is like 7 people on the bus. This is 14 people on the bus. This is 33. But over here's the peak, right? 150 people on the bus, 117, 143. That's how you interpret that. So let me set a couple constraints here just to line up the problem, and we'll execute it in just a minute. We have a bus capacity of about 50 people. So if we expect more than that, the demand exceeds 50, we're going to have to run at least 2 buses, maybe 3, maybe more. We're going to try to figure that out and solve that problem and optimize it too. Maximum buses per hour is going to be 12. One runs every 5 minutes. Okay, so 5-minute intervals. There will be 12 intervals in 1 hour. Minimum buses per hour is 1. Okay, so off peak, we're going to have at least 1 bus. During peak, we're going to have more. And the cost to run the bus in terms of the cost for the operator of the bus plus fuel that the bus consumes to run through the route is $40. Okay, these are just inputs, somewhat arbitrary, but pretty realistic. I think if you want to change it, by all means, go ahead and change that to what you think is more appropriate based on your city. I'm in New York City. The cost per bus might be a little bit higher. I'll be honest with you right there. Might be more like 50. I'm going to leave it at 40. This is just what I'm testing right now. But again, these should be realistic constraints. The more realistic you make the inputs, the more realistic the outputs. But again, if you want to change this to 50 or 60, if you think it's actually 60 per hour for the bus drivers, compensation plus the fuel that's consumed, plus repairs and maintenance on the bus, then go ahead and increase that, right? So I'm going to create a day forecast. This is going to be 1 day, so March 3rd, 2024. Okay, so everything between the beginning of the day and the end of the day, I want to use that as my forecast. And the value I'm going to try to predict is y hat. Remember, we have 2 values right here, or variables. The time series, that's the ds, and the y hat, that is what we're trying to predict. Okay, so we're going to set it up, make the prediction. This is going to be a linear programming problem. Okay, so I PuLP. This library right here helps me to run this, and I'm going to go ahead and minimize the bus frequency optimization. Okay, so if we maximize it, we can have hundreds of buses on the street. Is that going to help us? No, it's not going to help us. We want to minimize the number of buses on the street, but still handle the demand and meet all the constraints that we have to meet, right? So sending more buses during peak hours, fewer during off-peak hours, and making sure that we have these constraints met. At least 50 people can ride on the bus. So if we have a larger bus, and you will see these around New York City, there's buses that are almost the length of 2. So the capacity of those buses are much greater than 50. If you have one of those buses, you can substitute that over here. The maximum is going to be 12. That's a hard constraint right there. Minimum will be 1. That's a bare minimum that we need running at any given point in time. And the cost per bus, I'm saying it's 40. Again, that's debatable. It could be higher or lower. It's really up to you, whatever you think is warranted for your situation in your city, wherever you live. So I solved the problem. I get 1 over here. 1 means optimal solutions. So the solver right here did find a solution. So that's fine. So we have the model. In terms of buses, we're trying to minimize the number of buses. Buses goes down here, right? So linear programming on the number of buses times the cost per bus for H and H hours, right? So the cost per bus is 40, and the number of buses is between 12 and 1. So we solve the problem. If we get a 1 down here, that means it's optimized. So let me go ahead and print out the solution. So we have the hour of the day. This is midnight, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the peak rush hour over here. You can see that between about 7 and 9, right? Before that, it's about 100. That's actually a little bit before 7. So people are getting into the office a little bit early. Now 9, most people are in the office, and demand drops down by 10, kind of languishes a little bit down here, but by 3 p.m. it's starting to pick up. People are leaving the office by 4 p.m., 5, 6, 7, 8. By 8 p.m. it's dying down again, right? So we have a little spike around 5 to 7 p.m. And then it dies down at the end of the day. So let me go ahead and plot this, Control Enter to run the plot. We can see the capacity of the bus is in red right here, and the demand is a little bit more fluid, right? The demand is going to ebb and flow over time. The capacity of the bus really is much more linear and fixed and straight line, because remember the maximum is 50. So that's a hard constraint, right? But if we run multiple buses, we can accommodate more people. Over here, we have way more than 50 people, way more than 50, more than 50. So we need at least 3 buses at this time of the day, and 2 would just barely suffice. Over here, we only have a capacity of 50 people on bus. So here we have to run 3 buses. Here we'd have to run 3, or we're leaving people at the bus stop because they just can't fit on the bus, and people will get frustrated with that outcome, right? So you want to make sure you have at least enough people, at least enough buses to carry the people that are going to demand the bus ride, right? That's it. So here we have another plot showing, again, during the hour of the day, the number of buses that are running. So here's 1, 2, here's 2. Here's actually 3 buses, right? So this is 6, 7, 8, 9 o'clock. Most people are in the office, so we can drop the buses down to 2. This is early evening peak, so this is 3 p.m. People are starting to get out. By 4 p.m., people are wrapping up. We need 3 buses, 4, 5, 6, 7. This is 8 p.m. By 2000 hours, this is military time. 8 p.m., we need 2 buses, and down here, we just need 1. So let me show you one more plot here. This is the total cost to operate the bus. It costs about $1,800 per day to operate the bus, and that is just a flat expense, right? So the more buses we run, the more expensive it's going to be in terms of bus drivers, fuel consumed, even emissions spewed into the environment, right? All the pollution that's created. So we want to minimize the number of buses, but at the same time have enough to handle the demand, and have enough capacity on those buses to be able to take people from the origin where they start to the destination wherever they're going, right? And it costs about $1,800 per day to operate 1 bus, okay? So that is something just to be aware of. If we need more buses, we need it. If we can get away with fewer, so be it. We can do with fewer, right? So midday, late evening is a peak. Early in the morning, we see a peak. Costs stay pretty much minimized while preventing overcrowding, right? So this is what the model is doing for us. And this is exactly how transit agencies operate, or at least should operate. I'm guessing that they probably do something like this, at least some kind of version of this. Hopefully, if they're just running buses randomly, good luck with that. It's not going to work out too well, okay? I can very much guarantee you math is going to win every time. Statistics is going to win every single time. Computer science will win every single time, and finance will win every single time. If you're just doing it randomly, you are going to get slaughtered out there, okay? So you better have some kind of plan, because sooner or later people are going to be asking questions and you have to come up with answers, right? So this would be my solution for the problem right here. Optimized hourly buses. So we saw this before. Okay, so in the morning commute, 3 buses, right? In the evening commute, 3 buses from 4 p.m. to about 7 p.m. This is the graph that we saw before. So morning peak, evening peak, right there. We're just printing it out just for what is it? Not just for common sense. What am I trying to think of? Just for not even peace of mind. Just for sanity check. Sanity check. That's what I was trying to think of. Okay. So this is the sanity check printed out, and we saw the plotted version before. So what is the total cost of operating all these buses, and what is the optimized daily cost? Optimized cost is $1,800. Okay. Baseline buses per hour for all 24 hours. We have 3 buses. Baseline total daily cost is $2,880 if we didn't optimize. Okay, so this is the optimized solution, $1,800. We see that over here, $1,800. This is the optimized solution per day. Everything all inclusive, handle all the demand, all the buses for all the passengers. Now remember, this is Monday through Friday. This is work days, weekends. This could be a totally different schedule. I could have looked at that. I didn't even think about that. I'm just talking about it right now. I'm just looking at Monday through Friday. All right, that's why we see this morning commute. Saturdays and Sundays would be more flat, more plateau. You'd see like low ebbs and waves. This is definitely Monday through Friday commute time, right? So if you want to look at the weekends, the analysis will be slightly different. Everything in the weekend is different. People using energy, people commuting to the office, people working remote, people engaging in recreation activities, right? Monday through Friday, you don't see too many people out in the park throwing frisbees. On the weekends, you see that all the time. So people's behavior on the weekend is vastly different from people's behavior on the weekdays for the most part. I do have a couple of videos that explain how that works. I should have touched on this one, but I didn't think of it until just now. So the total operating cost for one day, again, Monday through Friday, $1,800. If we did not optimize, $2,880, right? So the total cost savings right here is $1,080 per weekday, okay? You're going to have about 252 weekdays in a year minus holidays, okay? I'm not counting Christmas, Thanksgiving, New Year's, 4th of July, what else? Thanksgiving, things like this, right? We have about 11 holidays in this country. I think it's exactly 11. And I know that because I look at the stock exchange. I worked on Wall Street for about 2 decades. We follow the normal holiday schedule. I believe there's 11. You don't have to work on the weekends, so Saturday and Sunday off. So 365 minus 252, whatever that is, that's about 100 something, 2, 3, 4, 5, 113 days, give or take, that you have off per year, whatever it is. You don't have to work those days. I only know that because I'm basing this on a Wall Street schedule, but most people follow that schedule. Whether you're on Wall Street or not, you kind of follow that schedule because you get those holidays and you get Saturday and Sunday for the most part. Not everybody, but most people, right? So the relative savings to this bus operating entity, New York City Bus Company, or whatever it's called, City Buses, something like that, 37% savings for optimizing the schedules here. If you didn't optimize, you would pay $2,880. With the optimized schedule, it's only $1,800 per day. And again, I'm saying 252 times 1,800. The total cost is, let me do this quick. I should have done that in the analysis, but I didn't. So these things I just think about when I start talking about it. So didn't occur to me before, but let me just do a quick calculation. 1,800, right? 1,800, 252. And then this is what? 28,280 to the right. Okay, this would be that times that, right? To the right. Okay. Oh, I did, wait, 28. Yeah, okay, that's why it's so close. That's why. Okay, so here's the total savings per year minus that. And this is what, one bus route, 272,000 that we're saving in 1 year just by optimizing the problem. So, these things look small. It looks like it's maybe nothing. There's not a huge savings, saving $1,800 versus 2,880, but over the course of the year, it adds up, guys. This adds up to be a big number, 272. I don't know how many New York City buses run. I really have no idea. If I had to guess, let me just say random number 252. It's going to be a big number, equals cost savings times the number of buses. And I don't know, I'm just guessing at this point. So New York City, if they optimize the schedule, can save $68 million per year. But I just made up this 252. I don't know if there's 252 buses that run around the city or not. I know there's that number of work days in here. I'm just using like some simple example. 252, that's a big savings, guys. It's a big savings just for optimizing the problem. No change in training. You're not hiring more people. You don't change the infrastructure. You don't change the technology. No IT investment, no hardware costs, no software upgrade, nothing like that. Just optimizing problem using math, statistics, computer science, and the bottom line is finance. Your capital gains is tens of millions of dollars, guys, tens of millions. So I'm going to go ahead and save this right here, HTML. I will share all the source code with you so you can drop it into your Jupyter notebook, drop every single block of code just like I have it, run it, and you'll get the same example I have. And by all means, change the hypothesis, change the example, change the inputs. The outputs will change, I guarantee that. And learn from the outcome, right? Play around with it, break it, fix it, tear it down and put it back together again, and you're going to learn a ton. When you do this all hands on stuff, you're going to learn a ton, guys. So that's it. That's my take on public bus frequency with passenger flow forecasting. That's my take on it. That's how I do it. So let me know your thoughts. Give me some comments in the comment section, and please subscribe to the channel. It really helps a lot. Thanks for your time, guys, and I'll see you in the next one. Bye for now.